Hi. Today we're going to carry on looking at circuit designs for our Eurorack project, which is going to integrate our big old test oscillators, our Marconi TF 1101s into a Eurorack format that we can then use live. And we are today going to look at designing a clock circuit to time our synthesizer, and within that clock we also want to be able to synchronize that clock to an external source, and we want to also divide that clock down into divide 2, 4, 8, 16. And to do that we're going to use 4 chips. We're going to use a 555 timer as our core to provide our clock pulses, our internal clock pulses. We're going to use an LM393 comparator to interface our internal clock pulses with an external source and then output whichever one we select. And then in order to do that will give us our clock pulse at our base timing. And then in order to get our dividers down, we're going to use a couple of CMOS chips. These are CD4013 flip-flops, and what these do is take a pulse in and then effectively divide by 2, and there are 2 stages of divide by 2 on each of these chips. So we'll get clock at baseline, so 1 to 1, divide by 2, divide by 4, divide by 8, divide by 16. And all the information that we need to do the 555 and the 4013s is in our trusty Bible by Don Lancaster. So let's just have a quick look at the 4013. Let's see if we can get it a bit closer here. Okay. So 4013 is a dual package flip-flop. And there's a whole bunch of things you can use these for, but for our purposes it's going to be pretty simple. We have one flip-flop on one side of the chip, one flip-flop on the other side of the chip. So effectively what this does in the mode that we're going to put it in is it takes a clock in this case on this side in pin 11. We'll wire up some of the others so that we get the desired result, but I'll talk more about that in a bit. And then on pin 13 and 12 it will alternate, so for a clock pulse, first clock pulse will come in on 11, it'll route it to 13, next one will be routed to 12, and then 13 and 12. So by monitoring just one of these you get 1 pulse for every 2 inputs, so it divides the input by 2. And then we can use that clock pulse to then come back into the other side to the clock and do the same again. So we'll get divide by 2, divide by 4, and then with another chip divide by 8, divide by 16. So that's effectively how we're going to do it. So if we were to just draw this out in sort of a functional diagram, what it would look like would be we have our 555, which is going to output a clock pulse, and this will be able to be varied, so we can vary the speed of the clock pulses, and we'll select some components to go around those chips so that we get the kind of output that we want in terms of clock speed. We're going to put that in then into a switch, and then from the outside we are going to be able to put an external clock which can come in, and we can switch it either between internal clock or external clock. In order that we can match the kind of voltage values and make sure that we get a good output from this section, we'll send that into our 393 comparator. And what that does is it says, well, if we've got a really small clock, for example here, a small voltage clock, the output will be a consistent. It'll compare it and then match it to an output value that we can select, which is then good for our onward chain. And then we send that effectively into our 4013 and another 4013. So from this chain of chips, if we were to monitor it here, we would get our clock at our baseline frequency. And then out of this one here, we would get divide by 2 and divide by 4 and divide by 8 and divide by 16. And then what I would also do when we come to the final build of it is that all of these we would then buffer. So we buffer all of these outputs for onward transmission and use then around the rest of the circuits that we're going to design. So that's kind of it in broad format. Obviously there's a little bit of work I need to do now just to make sure I know which inputs and pins and what other components we're going to need in order to make all this work. There's a few capacitors and resistors for both of these sides. So I'll get that figured out, and then I'll show you that schematic that we're going to use, and then we'll put it on a breadboard and we'll see whether it works. Okay, so I've done all of the design work I need to do, worked out a few component values, and then drawn it up in my proper notebook for reference when we come to build it. But effectively it's the same as a block diagram: 555, LM393, and then 2 CD4013s. I'm using standard logic voltages for the whole thing, just to standardise it, make it easy, so +5 ground. So here is our clock generator, here's our switch with our external clock coming in. I'll just put a little diode in there just so we protect the input. In then to the 393 comparator, and it's the relationship between this variable potentiometer and this resistor here that set the threshold at which the LM393 will fire. That allows us to do a little bit of fine tuning when we come to interface it with other bits of equipment we might want to use. And that then provides our first output and our clock out. You'll notice I've also added a little LED here so that we can actually see what our clocks are doing. I've chosen to use a NPN transistor here and tie that up to a 12-volt rail rather than using the output of the 393 itself driving from pin 1. And then really the implementation of the 2 CD4013s is pretty simple. No external components required. Tying a few pins together, tying a few others to ground, and then really the only pins that matter then are the input and the output. Input, output, input, output, input, output, which gives us our divide by 2, divide by 4, divide by 8, divide by 16. And that should work. So let me put that onto a breadboard. We'll fire up the oscilloscope and an external source as well, and let's see how we get on. Okay, I put all that on a breadboard now. Well, when I say I put it all on, I've only chosen to implement one of the 4013s. Only got a 4-channel oscilloscope, so but this will, so even if we put another one on, we wouldn't be able to monitor everything at the same time. But this will prove the concept at least. So we've got the 555 timer at the end here, LED showing us the speed of that, and a potentiometer to control the output of that one. That's going then into a comparator, the 393, and I've also got an external source coming in here which I can switch across between the two. And then we've got the 4013, so from this we should get clock, either internal or external, and then whichever one we have selected we should get divide by 2 and divide by 4. So let's have a look at the oscilloscope. So on the yellow trace there you can see the output of the 7 or the 555, I beg your pardon, and if I vary the potentiometer, you can see I control the speed of that. So let's just bring that up a bit, just so we get a few more pulses on the screen. Right, let's then have a look at the output of our first stage of the 4013. So this is hopefully divide by 2. And indeed we do have divide by 2, so 2 yellow pulses to every 1 blue. If we then look at the output of the second half of the 4013, this should give us our divide by 4. And yep, we get 1 pulse for every 4 yellows. So that all appears to be working pretty well. If I put the final trace up, this is the output of my external function generator, so another external clock if you like. Let me now just move across that output, or that input, I beg your pardon, and you can see that the 4013 is now tracking that one as well. So with a simple switch we can select between internal and external clock sources. Okay, well, I hope you found that useful. As I said, this is all part of an ongoing project which is hopefully going to culminate in the end with a large-scale synthesizer to control our big test oscillators that we're restoring. But that's another good functional component out of the way. Clock divider. So we'll move on to the next one in due course. Anyway, I hope you found that useful. Thanks for watching.